Hello everyone, welcome to our YouTube channel Electronics Maddie. In this video, we are going to talk about Thevenin's theorem, the theory behind it, and few of the solved examples with respect to Thevenin's theorem. So let's get started. Thevenin's theorem. So this is one of the most important theorems with respect to real life applications in electrical and electronics domain. So in order to not read the statement just like that, let us look at a pictorial representation and try to correlate what Thevenin's theorem is all about. So if suppose we have a network and RL is the load resistor that is connected to this network, and if they're asking us to find the current IL flowing through RL, in this case, what can be done is that you can have an equivalent representation according to Thevenin's theorem, that is a voltage source VTH connected in series with a resistance RTH to the load in this form. That is, this network can be replaced by a single voltage source and a single resistance branch in this way. So the purpose of doing this is very simple. If you're having a big network, you want to represent it in a very small fashion, like if a big network consisting of 4 to 5 sources and 3 to 4 resistance branches can be simply represented in this format, isn't it? It simplifies the way we look at the circuit. And if suppose the load keeps changing in real life application where this is applied, is that in transmission lines, in domestic applications where the current is applied to domestic applications. So there, if the load is changing, load keeps changing, isn't it? So the current also keeps changing, and we need to find out the current in each of the cases, and we cannot calculate and simplify the network every time. If we have an equivalent representation, we will be able to apply it directly with respect to the voltage source and the equivalent resistance that we have, and the current keeps changing with respect to it according to the load changes. So this simplifies the process of understanding how the network can be simplified. So what is the statement? Now let us try to look at the statement. Any two terminal network, if it is a two terminal network, it is only applicable to this, so be very careful with this point, can be replaced by an equivalent voltage source and an equivalent resistance, that is nothing but VTH and RTH. VTH is Thevenin's voltage and RTH is Thevenin's resistance. So the voltage source is the voltage across the two terminals with the load. So this is the voltage source across the load, that is VTH, that we are supposed to find if any removed. So the series resistance is the resistance measured at the two terminals when the load is removed, and constant voltage source being replaced by its internal resistance, and current source being replaced by infinite resistance. That means the resistance measured at this point is what RTH is all about. While measuring RTH, the current source and voltage source should be represented by their internal resistances, for that matter, either short circuit or open circuit. So in general, current sources are replaced as open circuit and voltage source is represented as short circuit. Why they are represented in this way? It is because current source, ideally speaking, with respect to the internal resistance will be very high, that is up to infinity. So that's the reason why we'll be representing as open circuit. With respect to voltage source, the internal resistance of an voltage source is equal to 0, hence it's represented as short circuit. But how do we proceed? How do we arrive at this from this network to this particular point? That is a big question, isn't it? So we'll be following a sequence of steps according to Thevenin's theorem. That is nothing but the proof of arriving at this particular point. We'll be following that throughout our problem. So let's look at the steps in Thevenin's theorem. Let us say this is the network that we have, and they've asked us to find the current flowing through the load resistance RL and represent this in terms of Thevenin's theorem. So how do we do it? First step is to remove the load resistance RL. That is the first step, and the network looks like this. We will be labeling that as VTH in this format, and we will be finding out the open circuit voltage VTH across points AB. There are network reduction techniques like KVL and KCL. We can apply them using Ohm's law. We will be able to find the value of VTH, and once that is done, find the resistance RTH as seen from the points A and B with voltage sources and current sources replaced by internal resistances. So that is nothing but the voltage source will be replaced by short circuit, and it will be represented with respect to terminals A and B. RTH should be viewed in this direction, that is indicated over here, and you will be finding out the Thevenin's equivalent resistance in this manner. So a quick note is that voltage source should be represented by short circuit, current source should be represented by open circuit, as already discussed in our previous slide. So once this is done, our next step is to replace the network by a voltage source in series with a resistance RTH. So that is done, and the load is connected now. So now what we will do is we'll be finding the value of current IL using Ohm's law. That is, IL is nothing but VTH by RTH by R plus RL. RTH and RL are in series, we are adding it out. So I is equal to V by R. That is the Ohm's law formula that is used over here. So we'll be able to find the current flowing through the load resistor RL. So this clearly simplifies, isn't it? If the load keeps changing, you can simply find the value of IL by replacing the value of RL that is changed. So that's where Thevenin's theorem plays a prominent role in respect to real life applications. So I hope this concept is clear. Now we'll be looking at three different problems, and the approach will be with respect to the same steps that are there over here. So let's get started with the problems. We have the first problem. They've given us a network and they've asked us to find the value of current flowing through the 2 ohm resistor. So this is the 2 ohm resistor. So as usual, we will be starting off with our initial steps, calculation of VTH, how it can be done. We will be removing the 2 ohm resistor from the network, and we will be representing the equivalent circuit. Draw the equivalent circuit in each and every case, because you will not go wrong while indicating the directions and the symbols with respect to the convention that we have followed. So we are following, when the current is entering, we'll be considering it as positive, and it is leaving, it will be taken as negative. So we'll be writing plus and minus across the points that is required, so that it will be easy for us to apply KVL and not do any mistakes while doing that. So applying KVL to this particular mesh, so there is only one mesh with respect to it, because no current flows here, because this is open circuit. So remember this point. So current enters at 40 volt and lives at positive terminal, so we'll be writing plus 40. Now again current enters 5 ohm resistor and lives at minus 5 ohm, so we'll be writing minus 5 into I according to Ohm's law. Now again current enters plus terminal and lives at minus, so we'll be writing minus 20, and in this point we can directly write it as minus 10 amps, because 10 times I, because 10 ohms is the current flowing and current enters and lives at minus terminal. So we'll be equating it to 0, because according to KVL the algebraic sum of EMFs in a closed loop is equal to 0. So our next step is to simplify this. We will be writing simplify this, and we'll be finding the value of I, that is nothing but 1.33 amps in this case. So once this is done, we will be writing VTH equation, which is very important. We are supposed to find VTH, that is our objective, isn't it? So what is the voltage that is appearing across this point? Isn't that's a big question. So we will be looking at this network in this direction. So again, if the current 10 amps, the current I is the flowing current, if you are assuming it to be, since this is the point where you are assuming, there will be some amount of current flowing through 10 ohm resistor. So 10 plus minus to plus, so current, if you, this is not a closed loop, but we can find the voltage at this point by considering the current that is flowing because of this loop. So you'll be having 10 amps that is flowing from minus to plus in this direction. So I mean, you have to write it as minus here and plus here, and just to see, not get confused with respect to it. 10I minus VTH, so plus to minus, minus is the point we are considering, so minus VTH, again minus to plus, so plus 10 volt is equal to 0. We'll be writing the VTH equation. So VTH will be given as 10 times I plus 10. So substituting the value of I, we'll be getting the value of VTH, that is equal to 23.33 volt in this case. So once we have found out our VTH value, the next step is to calculate the value of RTH. How that can be done? Replace voltage sources by short circuits. We only have voltage source in this circuit, so there is no current sources, so we'll be replacing all the voltage sources by short circuit. So once we replace it, and we'll be finding the resistance across the point AB, that is according to the current supposed to be flowing through the 2 ohm resistor, and we will label it as RTH in this direction as indicated. Now we have to find the effective value of resistance at this point. We see 5 ohm and 10 ohm are connected in parallel. Just tilt 5 ohm in this direction, and you will clearly observe 5 ohm is connected and 10 ohm is connected between the same 2 points over here. So that is nothing but RP is equal to R1 R2 by R1 plus R2. I have substituted and found out the value as 3.33 ohms. Step 3 is to calculate the value of IL. So how do we do that? We'll first draw the network. This is the Thevenin's equivalent circuit. You can also call that that way. So you have 23.33, that is VTH, that is in series with 3.33, that is RTH, that is in series with the load RL, that is to be calculated. So IL is the current flowing. We are supposed to find the value of current flowing through 2 ohm resistor. 2 ohm resistor. So the current flowing in this branch can be obtained by using Ohm's law, that is nothing but V by R. R in this case is nothing but series combination of 3.33 ohms and 2 ohms. Since same current flows through both of them, we can add them up and find the value of IL. That is nothing but 4.38 amps in this case. So that is what is the question, and we have found out in this particular sequence. These are the sequence of steps that we have to follow. Let it be in the same sequence, so that we do not go wrong in any of the steps that is there. So I hope this example is clear. So let's look into another problem. Find the current flowing through a 2 ohm resistor resistor that is indicated over here. So pause this video and try this example on your own. It is quite similar to the previous one. So this would help you practice a different problem with respect to the previous one. So with respect to this, now let's get started. Step one is to calculate the value of VTH. That is our normal step that we do, removing 2 ohm resistor. That is, this is the 2 ohm resistor over here, and connected between A and B terminals. So we will be removing that and we'll label that as VTH. Now our first and foremost step is that we'll be applying KVL to mesh 1. So we see that there are two meshes in this case. Current, this is one loop, and again this is another loop, the outermost loop. So there are two loops that are there. So we'll be applying KVL to mesh 1. In this case, if you see, we have considered the direction to be in clockwise direction, so you can consider it in anti-clockwise as well, but suitable assumptions with respect to sign should be made. So our first step is the current is entering 2 volts, so that is from minus to plus, so we'll be writing plus 2. Again, with respect to resistor, plus to minus, so minus 2 times I1, and now again plus to minus 12 times is the value of resistor I1 minus I2, because we are considering this mesh. So that is equal to 0 according to KVL. We can simplify this and we can write this as equation 1. Applying KVL to mesh 2, similarly we can write it as in this way, that is minus 12, that is from plus to minus, minus is 12 is the value, and I2 minus I1, because we are applying it with respect to mesh 2, so you will be getting this minus 1 times I2, that is because the current enters at positive and leaves at negative. When it is living at negative, we'll be writing negative sign here, and the value of resistance is 1 ohm and the current flowing is I2, so we'll be writing it this way. So minus, that is again from plus to minus it will go, that is with respect to 3 ohms, and current flowing is I2, so we'll be writing minus 3 times I2. That minus, again because of the current flowing from positive to negative, it lives at the negative terminal of the battery, that is equal to minus 4, that is equal to 0. So the algebraic sum of EMFs in a closed loop is equal to 0 according to KVL. So simplifying this expression, you will be arriving at this point. Again, this can be labeled as equation 2. Solving these two equations, if you substitute in calci, or you can apply different methods like matrix method to solve these equations, you'll be getting I2 is equal to minus 0.4 amps. So this is what our intention was all about, to find the value of current I2. Once this is done, we can find the value of VTH. How can we do that? Just observe this carefully. Writing VTH equation. So at this point you have to find, right? So at this point, how can you find? You know that I2 is the current flowing through this loop. That means I2 is flowing through 3 ohms as well. So that is nothing but, if we are keeping VTH at this point, so this resistor and this source is connected in parallel to VTH. That means VTH, if you are going in this direction, that is plus VTH minus 3 into I2. Again, plus to minus 4 is equal to 0. So we are writing VTH and we are representing VTH is equal to 4 plus 3 times I2, and that's the reason why we wanted I2. Once we know the current flowing through 3 ohm resistor, the voltage that is appearing at this point will obviously be the voltage appearing at the effective combination at this point. So VTH is equal to 4 plus 3 times I2. So we'll be substituting the value of I2 and find the value of VTH. So VTH is equal to 2.8 volts in this case. So step 1 is finding out VTH, and we have found out. Now let's go to step 2. Step 2 is to calculate RTH. What we will be doing for calculating RTH, we will open circuit that particular terminal and replace the voltage sources by short circuit and current sources by open circuit, and that is what is shown. The voltage sources are all short circuited over here, and now we'll be finding the value of the effective resistance. That is nothing but, we have to simplify this. 2 ohm and 12 ohm are connected in parallel, so you use the formula of RP equal to R1 R2 by R1 plus R2. Find the effective value. Again, the effective combination of 2 ohm and 12 ohm connected in parallel will be in series with 1 ohm. Add that with 1 ohm resistor. Again, the overall combination will be parallel with respect to 3 ohm. So once you get this value, you have to do again the parallel combination formula. RP is equal to R1 R2 by R1 plus R2. That is simply represented in this form. If you have any doubts with respect to simplifying these resistance connected in series or parallel, refer to my previous one of my previous videos, that is with respect to simplification of series and parallel resistors. That will give you a clear picture of how to solve these type of problems. So you'll be getting RTH is equal to 1.43 ohms in this case. Step 3 is to represent the Thevenin's equivalent circuit and calculate the value of IL that is flowing. So VTH is 2.8 volt that we have got, and RTH is equal to 1.43 ohms, and the load resistor RL is equal to 2 ohms in this case. That is what is asked for us to find the current flowing through 2 ohm resistor. IL is equal to 40 by 5 plus 1.67, that is equal to 0.82 amps is what that we are getting. So the current flowing through 2 ohm resistor is equal to 0.82 amps. Similarly, if they change the value of resistor, say similarly find it for 4 ohms also, you bring the Thevenin's equivalent circuit and replace the value of RL. That's all. The steps, all that is done previously can be retained, and only step you have to do is change the value of 2 ohms to 4 ohms if it is asked for 4 ohms. That's it. So this is how Thevenin's theorem is helpful, isn't it? So once this is done, I hope these two problems will give you a great clarity, but we'll also go for another type which has a current source as well. So example 3 contains a current source, and it is asking us to find a value of current flowing through the 10 ohm resistor. So again, this has the same steps that we have followed in the previous problem. That is, step 1 is to calculate the value of VTH. How that can be done with respect to 10 ohm resistor. This is at this point, remove that, open circuit that, and find the value of VTH at that point. So how do you do that? There are two loops clearly over here. No current flows through this point because this is open circuit, so we have left that as it is. So our first step is for mesh 1. We can directly get the value of I1 as 10 amps because the current that is flowing in this loop is nothing but 10 amps, because there is no current flowing in this path, so there is no current entering in this direction. So whatever current is flowing will be flowing through only 5 ohms in this case. So 10 amps flows through 5 ohms resistor, so I1 is written as 10 amps. So similarly, now for applying KVL, now we'll be applying KVL to mesh 2 with respect to this. So what happens here is that we will be slowly going step by step here. 100 ohms, if you are applying from minus to plus, so it's plus 100. Again from plus to minus, so minus 30 I2. Again from plus to minus, that is minus 20 I2, that is equal to 0. Algebraic sum of EMFs in a closed loop is equal to 0. So we'll be simplifying this. You'll be getting I2 is equal to 2 amps. So we have got the value of I1, we have got the value of I2. Now the simplification will be much easy. That is, we'll be writing the VTH equation. So VTH equation with respect to it is nothing but at this point. So what is the current, what is the effective value of the voltage that is appearing at these terminals? So how do we find that? That is nothing but the if you consider this as one path, although no current flows, but current flows through 5 ohm because of the loop 1, and current flows through 20 ohm because of loop 2. So considering in that way, 5 amps is the current flowing with respect to this loop. If you are considering minus to plus, plus 5 5 I1, plus to minus, minus VTH, and plus to minus, again it will be minus 20 I2. I2 is the current flowing through 20 ohms, so I have written that way, and that is equal to 0. So be very careful with respect to writing VTH equation. KVL cannot be applied with respect to open circuits, so that step is to be remembered. We cannot write applying KVL to this particular portion or something like that. This is nothing but mentioned, that can be mentioned in this way, is that we have to write it as writing VTH equation. So once that is done, we'll be finding the value of VTH by substituting the value of I1 and I2. We'll be getting the value of VTH to be 10 volt. So next, step 2 is to find the value of RTH, that is replacing current source by open circuit and the voltage source by short circuit. As I told earlier, current source is represented by open circuit because the internal resistance that is there for a current source is very high, and the voltage source internal resistance is very less, and it's ideally assumed to be a short circuit that is equal to 0 ohms. So the resistance is replaced in this, the once replaced by short circuit and open circuit respectively. Now we will be finding the effective value of resistance at this point. From here you can see 30 ohm and 20 ohm are connected in parallel, and the effective combination will be connected in series with 5 ohm. So I have written 5 plus 20 parallel to 30. Simplify this and you will be getting 70. So step 3 is to calculate the value of IL. Again, we'll be representing Thevenin's equivalent circuit, that is 10 volt connected in series with a resistance RTH, that is 17 ohms, that is already found out, in series with a 10 ohm resistor, that is the current that we are supposed to find out. And we'll be getting the value of IL as 10 by 17 plus 10, that is V by R. With respect to Ohm's law, we'll be getting 0.37 amps. I guess we've solved a lot of different varieties of problems with respect to Thevenin's theorem application. There are still a lot of varieties. Please do practice a lot of different problems with respect to Thevenin's theorem. In case you have any questions, please feel free to reach out to me with any questions that you have. If you like this video, please do like it, share it, and subscribe to our channel for regular updates. Thanks for watching this video.